In this presentation, I will mostly talk about rooms with absorbent ceiling treatments and how we try to estimate and characterize those rooms by using different type of room acoustic descriptors. But nevertheless, first I will just say a few words about concert halls. And it's no doubt that if you try to characterize a concert hall, then we need several quality aspects, and those are from a paper by Baron, and he states that you need at least 7 different measures to probably characterize a concert hall, related to clarity, to reverberance, intimacy, source broadening, and loudness. And I guess he especially emphasized loudness. And all these measures are also quite well specified in the ISO standard 3382 part 1. And also, in fact, with some figures about just noticeable differences. So there is quite a large work done when it comes to concert halls. But now, if we look at our ordinary rooms, like schools, offices, and hospitals, well, it's more about reverberation time, still. Even since it was more than 100 years since Sabin's discovery, it's still the dominating parameters in recommendations and standards. There is one exception, and that is the new office standard, where there are other measures. In fact, the reverberation time is not included at all. So that's quite a large difference. So quite a lot of people are working in these areas, and we simply try to evaluate it by simply using one parameter, the reverberation time. Why do we need more parameters for these type of rooms? I will just start with showing you an example of a measurement that we perform in these 2 quite small meeting rooms. They are the same size, the same volume, the same height. The only difference is that in room number 1 here, we have an absorbent ceiling with highly efficient absorption, alpha value almost close to 1. And in the other one, we have a more reflecting ceiling with an absorption coefficient 0.1, a weighted one. Of course, this is a little bit exaggerated situation. There is no furniture, but this is, nevertheless, I will show you the results. And we also did a sort of a questionnaire. We have a few subjects that go into this room 2 at a time, and they try to judge different quality aspects. For example, if they find the room distinct or indistinct. If they find it extremely indistinct, they put a cross mark here. And if they find it very distinct, they put a cross mark here. And then we go through all the different ratings, pleasant, unpleasant, and so on. I will not go into detail here, and this is maybe not very scientifically, but nevertheless we get some responses from all the subjects. And as you can see, here we have the number of votes, and here we have the ratings. And the red one is room 2, and the blue one is room 1. And as you can see, when it comes to distinct and indistinct, it's a quite clear difference. And I will go quite rapidly through all the other, and you can just look at the graphs and you see dry, reverberant, best possible listening environment, worst possible, and so on. It's quite clear just from the figures that the subjects, they notice a difference, for sure. Then we did some typical room acoustical measurement in these 2 rooms. We measure the impulse responses, and we calculate the reverberation time, and we also calculate the speech clarity and the loudness level, the sound pressure level in the rooms. And when we look at the reverberation time, we got this figure, which might be a little bit surprising. As an acoustician, you maybe, well, there are some differences, some frequencies, but they are quite similar, which maybe is a little bit surprise. But that's what's happened. But now, if we look at the C50, then we got quite clear differences of several dBs, in spite of the fact that the reverberation time were more or less the same. And then we measure the sound pressure level. We put a constant sound power source into the rooms and measure the level, and also here it's a clear difference between the two rooms. But as you see, we don't see those differences in the reverberation time. But of course, now we have no furniture in the room. If we put in some furniture, then we will see a little bit difference in the reverberation time, but we will never get those differences that explain the differences that we get in speech clarity or sound pressure level. We also did another small experiment that we put in some wall panels, just 4 patches, 600, 600 into this one room number 1 here with the highly absorptive ceiling. And then you see only this small amount have a quite large effect on the reverberation time. And even on the speech clarity, but not that much on the sound pressure level. So you see that it's really a need for more parameter and reverberation time to explain all this behavior. Okay, so our conclusion is that at least it could be good to evaluate this type of room with ceiling treatment with the reverberance, the speech clarity, and the auditory strengths. For more open plan spaces, there are some other measures, but I will not go into that now. So then, of course, from engineering purpose, it's quite good to be able to estimate those parameters as well. And we have, as you know, formulas for reverberation time, but not that much for speech clarity and strengths. For concert halls and large spaces, there are a model developed by the Baron for calculating the strengths. And knowing the strengths, it's also possible to calculate speech clarity values. But we have no such a model for the rooms with absorbent ceilings. But I will try to present an idea for such a model for these type of rooms with ceiling treatment. So if we start with the Baron's model, it's a model that calculates the strength value, and it's based on that he calculates the integrated energy for the early and late part of the impulse response given by those expressions, and he also included direct sound. And then simply add all those values and get the strengths in a quite nice and simple way. But still, this is based on diffuse field theory. And as you can see, it also assumes a linear decay. We have the reverberation time here. So it don't work directly for rooms with ceiling treatment. Because if we look into rooms with I will also say that it's knowing the sound strengths here and knowing the energy of the early and late part, then it's quite simple to calculate the speech clarity, because that's simply a ratio between the early energy and the late one. So you simply have the factors here. And even if you change the time limit to some other values that we heard yesterday, 35 or whatever, 80, it's just to put in the formulas. But if we look in a room with absorbent ceiling, we can see that we can assume that is composed of a large of modes, waves, with energy but also with different decay factors, because as you know, the waves that hits the wall are normally less damped than the waves that hits the absorbent ceiling. So the total decay curve can be composed of all these individual decays. And a typical behavior is that you get a curvature of the total decay curve. So in fact, you don't really have a very well-defined reverberation time, because it's more sharp, more in the beginning it's a shorter reverberation time, and then you have a longer reverberation time at the end of the curve. So the idea that I used to describe this behavior, I will also say that it's, I mean, okay, this can maybe be done in a rectangular room with only ceiling treatment, but if you introduce furniture and scattering, then this becomes quite complicated, because then they will be altered, all these waves. So an idea is here to divide the sound field in these rooms into two parts. One part dealing with the late reverberation time and one with the early part, calling grazing and non-grazing wave. So this non-grazing part, we can say, correspond a little bit better to the Saint-Gobain assumptions than the grazing. But here, of course, we have to estimate the decay factors for these two slopes. But not only the decay factors, you also have to know the energy to get the strength value. But one advantage with this approach is that scattering could be, what should I say, handled quite easily, because we can assume that scattering could be interpreted as an energy transfer between the grazing part and the non-grazing one. And that could be quantified. So that makes it a little bit more easy to handle. So, and using this, so to say, the same approach as Baron, creating expression for the integrated energy for the early part and the late part, we get a little bit more complicated equations, because in this case now we have two decay factors, one for the non-grazing and one for the grazing. But we also need to have some factor that estimate the energy ratio between those two fields. But it's nevertheless quite simple expression, and you can put them into this formula and you get the strength and you get the C50. But of course the tricky part now is to estimate the non-grazing and the grazing reverberation time and also the energy ratio. So, I will not go too much into detail, but nevertheless show you the idea how to estimate those values. And when it comes to the grazing reverberation time, one way is to assume a two-dimensional diffuse sound field. Like the Saint-Gobain is a three-dimensional diffuse sound field, we assume a two-dimensional. That's why we have another factor here. But the most important thing here is that, here we can include an equivalent scattering area, meaning that, because the interpretation of scattering here is that if we put furniture into a room, the main effect will be to, as I show you, convert energy from the grazing field to the non-grazing. Then I will show you later, we can estimate the scattering. Another thing here is that, as you know, for a sound field that is more or less horizontal in the room, we can't use the normal absorption coefficient for the ceiling, because it's more the grazing part is the angle dependent for very grazing incidence that goes into this equation. So there also have to be some way to estimate the angle dependence for grazing incidence. When it comes to the non-grazing part, it's more or less like Saint-Gobain's formula. So here you have the normal absorption coefficient for the ceiling, for the furniture, and for other surfaces. And then the factor that gives the energy, so to say, between the grazing and non-grazing field, that is the reverberation time, and this is the number of modes in the grazing, and this is the number of modes in the non-grazing. So there's also one part of where we have to decide how to divide the sound field into a grazing and non-grazing part. So there are some considerations, and I will just mention, first I will just show you a quite simple way to estimate the scattering. And the scattering here is expressed in an equivalent scattering area, like we have the scattering absorption area for absorbers. And the idea here is to measure in a room, rectangular room, with a highly absorptive ceiling. And then we measure without furniture, and then we measure with furniture, as we do with our absorbents. And then this will at least give an estimate of the scattering, but we assume here that all the waves that are scattered are trapped in the absorber. Of course, some are reflecting, but we ignore that one. So this is the one I have used to estimate the scattering. Okay. So then there are some other considerations that I will not go into detail here, but what we need here in order to be able to, for example, estimate the grazing absorption, then the description of the ceiling absorber is the impedance. And for porous absorbers that is quite easy because that is related to the airflow resistivity. But that is quite good to have, because if we know the airflow resistivity, then we can fairly easily calculate effects with different mounting heights, the effect of the air cavity behind the absorber and so on. Then there is a definition of the angle sectors between grazing and non-grazing incidence, and here I use some so to say wave theoretical estimations where you can estimate the angle for the most grazing mode groups. So there are expressions for that, so you can calculate every step, and then when knowing that, then you can calculate the number of modes in each group. And for each group, then we can estimate the absorption factor, the grazing absorption factor, both at high and low frequencies. And some other consideration is that, of course, it could be tempting now for the non-grazing group that is quite similar to the Saint-Gobain assumption that we could use the statistical absorption coefficient. But assuming diffuse condition means that if we look at the energy as a function of angle of incidence towards the ceiling absorber, we have in a diffuse field we have a distribution that is more or less focused on 45 degrees. But if we look at ordinary rooms and look at how the energy is distributed, it's differ. So that means that even for the non-grazing group, we don't use the statistical absorption coefficient. Instead, we use an absorption coefficient corresponding to this angle. Another thing that is also I have seen when we do compare with real measurement is that sometimes at low frequencies there seems to be an idea to take into account the air cavity and the way the absorption process is going on. As you know, normally we say that we call a porous absorber local reacting, and that the sound field comes here and then the absorption goes in the normal direction. But in practice, it's at least at low frequencies we see an effect of the refraction. It's called extended. But since we have the impedance as a description of the ceiling absorber, it's quite easy to take that into account as well. Okay, now I will show you some real cases. This is a classroom with a volume 150 cubic meters, and in the ceiling here we have a 50 millimeter porous absorber, and it's, the airspace is 0.75 below the soffit. And I have to say, when I did estimate the scattering, we did the measurement with and without furniture. So of course I used the value that is measured in the room, so that helps to get a good prediction, of course. But I think that this could be done separately. And the furniture here, as you can see, it's a table and chairs and typical classroom furnishing. So if we look at the results, it looks like this. If we look at the reverberation time, the blue one is measured, the green one is calculated, and the yellow one here is the Saint-Gobain. And you can see there's a quite large difference for what we measure and what we calculate by Saint-Gobain equation. It really don't work in this type of rooms. And but you can see it's a quite good correspondence. And if we look at the C50, then we also see that the diffuse field theory really overestimate the C50. But here we got quite a good correspondence. I don't know what happens with 250 Hertz, but there are some differences. When we look at strengths, the differences is not that large, as we heard Jack Harvey talk about yesterday. And that because when we measure strengths, we normally have a constant sound power source, and that means that during this type of measurement, steady state measurement, the sound field is quite diffuse, even if we are in a room with ceiling treatment. So, but nevertheless, there are some differences, and the diffuse field theory a little bit overestimate. The green one's calculated one is a little bit lower, but yeah, quite close. And then the next case is a little bit more tricky. This is a small meeting room, and 74 cubic meters, and it's the same table and chairs, but organized in another way, like a U-shaped conference settings. And here I also tested with and without wall panels, and that is quite interesting because I can show you the results here. This is without wall panels, and yeah, you can see this is quite good correspondence. And of course, this very much depends on that I use the scattering measured in these rooms. So, and you can also see that the reverberation time by Sabin is quite low, and also it's you see the diffuse field theory. It gives another shape. It's not, but the frequency dependence in these models is more correct. So this is quite okay. And then I put in the wall panels. As you saw, it was can go back. It was in fact 5 quite small pieces, 600, 1200, 40 millimeter absorbers on the walls, only on that wall. And here we have the results, and this was a little bit more tricky. As you can see, we still get better correspondence than the diffuse field theory, but we have some discrepancies here. But what is interesting to see is that when we have this subdivision into the grazing and non-grazing field, then the effect of the wall panel is more pronounced in these calculations than if you do a Saint-Gobain calculation, because adding the wall panels in the Saint-Gobain calculation, you don't see it. It's too less area. But the real effect is that, as you saw in the demonstration, it's quite huge, and that is what you see in this model. But I think it's quite interesting that you see that the calculation here is a little bit lower than the measured one, and the reverberation time a little bit higher. And I believe that depends on that I have used here when I calculate the absorption for the wall panels, the absorption coefficient measured according to ISO 354. And you know that if we measure on large spaces or small patches, that will have a difference. So I think that this is a little bit of an area effect that we see. But that is something we can compensate for, taking the area into account. And the effect, if I do that, will be that we will get an improvement of the absorption coefficient here. The strengths and the reverberation time will be a little bit lower. But that's quite interesting because we can see those effects in these type of calculations, because the wall panels acts more on the grazing field than on the non-grazing. So the conclusions is that I think it's quite clear that we really need more parameters than the reverberation time to evaluate acoustics in rooms like classrooms, offices, and this type of rooms with ceiling treatment. I think speech clarity and sound strength seems to work quite well, and we can estimate them as well. But of course, I think the main importance is that we measure at least parameters that are related to speech intelligibility or are related to the noise levels. And for engineering purposes, I think this subdivision into a grazing and non-grazing works quite well. But what is quite important is that we have a method to quantify the scattering of furniture. And the way I did it here is quite simple. I mean, I think sometimes in standards it could be good to have methods that is quite close to reality. I mean, we have this ISO 354 standard where we measure the absorption coefficient, but that's quite special conditions. It's a diffuse field, it's a reflectors, it's a small area. It differs quite a lot from what we have in practice. But there are other examples of standards where you get closer to the, so to say, the real situation. Like in ASTM, we have measures for measuring articulation class and such, so we build this type of mock-up. And I think to measure scattering, we can use this type of rectangular room with a highly absorbent ceiling and measure the objects and then define a sort of alpha scattering per object. And then we can use that in this type of models. So, thank you very much for your attention.